very glad. Okay. Third time's the charm. Thanks so much for the invitation. I'm very glad to be here. Today is going to be an intro workshop to Bayesian statistics in R. Before we start, I just wanted to say, whenever you have a question, so I'm going to talk a lot during this workshop, but whenever you have a question, please just write a message in the chat. I will try monitoring it. The other organizers will also keep an eye on it. If I miss any of your questions and you think, oh my God, now I don't understand anything anymore, and I really need this question answered right now, then please just unmute yourself and ask. This is supposed to be interactive. I hope we can make it that way. Yeah, I was told to talk a little bit about myself at first and where I'm coming from. So as you might hear from my accent, I'm of German origin. I come from a small town close to Munich. And I have to say that after high school, I was convinced that I would never learn how to program and that I could throw my calculator in the bin. I loved traveling, I loved learning languages, and so I was convinced that I would study humanities. So I started studying cultural anthropology at LMU Munich. But after a year, I realized that I'm more of a quantitative person than I thought. And that I actually like solving scientific arguments with numbers rather than angry letters. So I switched my major to psychology, where I love the quantitative approach in the social sciences. And to my own surprise, I even loved my statistics classes. But I also realized that quantitative methods in the social sciences are not as unequivocal as I thought they would be. So particularly in social and organizational psychology, where I did my master's. Social psychology, I don't know who many of you know, is going through a crisis called the replication crisis. And this crisis is partly caused by the fact that statistical methods weren't applied with sufficient care, that scientific scrutiny was sacrificed for flashy results. And so people just lost trust in the discipline. And this whole situation made me really frustrated and brought me even closer to statistics and psychological methods. So at some point, someone told me, like, hey, there's this new branch of statistics, and it's called Bayesian Statistics, and it can solve all your problems. And naturally, I was intrigued. So I tried to learn more about it, which brought me to the University of Amsterdam, first just for a research internship, but then I decided to stay here to keep working on Bayesian methods during my PhD. And at this point in time, I have to say, personally, I don't think that Bayesian statistics is the panacea for all problems in the social sciences. But personally, I find it just very appealing because for me, it is the statistical approach that captures best how we gain knowledge in any domain of our lives, which also includes science. So for me, this makes Bayesian statistics very intuitive on a conceptual level. And for me, it's becoming increasingly difficult to think about learning from data in almost any other way. And so this is also what I want to talk about today, and why I want to bring Bayesian statistics a bit closer to you. So this means that today we will be going back to the roots of R. I know that we all nowadays use R as kind of a Swiss knife for all kinds of data applications, like data cleaning, visualizing, making predictions using machine learning, creating dashboards, writing manuscripts. But originally, R was developed as a statistical programming language, and that's what I want to use it for today, to explain the basics of Bayesian statistics to you. Now, there are many ways to start out in Bayesian statistics. It's a huge field, and depending in which area you're working, say medical statistics, engineering, business administration, you will encounter different tools, different methods within the Bayesian framework. So there's no way we will cover all of this in 1.5 hours. So what I want to do today is to stick to the very basic concepts that I think occur in almost every more specific textbook or article that you may read within your field. And the idea is that after this workshop, you will be able to read more advanced materials, to recognize these key concepts. And if someone presents you with a new Bayesian method or applied a Bayesian method to an application in your field, then you kind of know the mental model that they have about statistics, and you can ask them specific questions. So that's our goal for today. So enough of the introduction, let's get started. You should all have a link to a GitHub page where you can find these slides and also a short R script that I'll walk you through today. Maybe someone can also post this link in the chat. But yeah, we won't need the R script for now, because I want to start with a very, very broad introduction so that you get an impression of what we will be talking about today. So Bayesian statistics is a framework in statistics that is getting more and more popular. You can see that there are a lot of articles written about Bayesian statistics in a lot of fields. Bayesian statistics has even made an appearance, actually 2 appearances, on popular TV shows such as Big Bang Theory. And it is presented as something that is, well, the new statistics. But actually, Bayesian statistics is nothing new. So the first one who came up with it was Reverend Thomas Bayes, who was a Presbyterian minister, lived in the 18th century. And he is the person behind Bayes' theorem, which you might have heard about. The other important founder of Bayesian statistics is Harold Jeffreys. He was a true jack of all trades in sciences. He was a geophysicist, mathematician, astronomer, and he is the one associated with Bayesian hypothesis testing. So if you ever hear about Bayesian hypothesis testing, Harold Jeffreys is the person who laid the foundations. Bayesian statistics is about quantifying uncertainty. So this is the true core of Bayesian statistics, is that we want to quantify uncertainty. And the underlying idea is a specific idea about probability, and that is, I think, very well represented in this quote by Jevons. He said, "Chance exists not in nature and cannot coexist with knowledge. It is merely an expression for our ignorance of the causes and our consequent inability to predict the results." And so this means if there was no uncertainty, there would be no use for the concept of probability. We can also give a more modern explanation. Say you compete in a quiz show and you're presented with this question and you don't know the answer for sure. And so you say something like, well, the answer is probably B. Now, what does probably mean in this context? It's not like every second time the answer is B, but there is a clear true answer. You're just, by expressing a probability statement, you are expressing your uncertainty about the true answer in this question. And this is also the underlying idea about probability in Bayesian statistics, that we use it to express uncertainty. Now, there's another core principle in Bayesian statistics, and that is Bayesian statistics is all about updating knowledge. So what do I mean with this? You start out with some prior knowledge, something you've heard, something you believe in, some model of the world that you have, some theory, some hypothesis, and you can use this prior knowledge to make predictions. And then you compare these predictions with what you see in the world. So for example, I can believe that it will rain tomorrow, and then I can compare my beliefs with what actually happens in the world. And what I see in the world will update my beliefs. And I will get new beliefs from which I can then again compare with what's happening in the world and keep updating my knowledge. And this is also what I meant at the start. This is, at least for me, it's very close to my mental model of how we learn about things in the world. We start out with some knowledge or no knowledge, and then we make observations, we compare them with what we believed before, and then we update our knowledge. Now, knowledge updating happens in Bayesian statistics, kind of happens in two realms, so to say. And that is parameter estimation and hypothesis testing. And you might know these also from other branches of statistics, maybe from your statistics lectures in undergrad. And I think it's, you don't have to stick to this separation, but it's a nice way to think about where, in what areas can you update knowledge. And today I would also like to stick to these two realms and look at each of these separately in the remainder of the workshop. And yeah, we will start with parameter estimation. Maybe so far I should take a look at the chat. Did anyone ask a question?
No questions.
No. But does anyone have a question so far? No? All right, then I'll just keep talking. All right, I said we were going to start with parameter estimation, but I think we should start with what even is a parameter. And because there might be different, depending on where you work, there might be different interpretations on this. So what I mean with a parameter is any measured quantity of a statistical population that summarizes or describes an aspect of the population. So for example, this means the mean, a standard deviation, a variance, a proportion, anything that can describe your population. Now, the issue in real life problems is usually we don't know our population, and often we cannot get even close to it. And so the question is, how can we gain knowledge about our population parameter? And this is what we do in parameter estimation. Now, in Bayesian statistics, there are a few concepts associated with updating knowledge in parameter estimation, and I'll just walk you through them in the next, I think, probably like half an hour. We'll do a break afterwards because this might be a lot to take in. So at this point, I also want to remind you that whenever you have a question or whenever you feel you're dropping out or getting confused, then please let me know. So we will do this. We will go through these concepts using the idea of knowledge updating. So we want to start with the Bayesian concept in prior estimation, in parameter estimation that represents our prior knowledge. So the knowledge that we start with, and that is the prior distribution. In the following, I will use an example. So this running example will be about cat people and dog people. I don't know who of you owns a pet, but there are a lot of articles out there, and even some scientific ones, but mostly not so scientific ones, that claim that people can be divided in two groups. People who prefer cats over dogs, that's cat people, and people who prefer dogs over cats, that's dog people. And the example I want to use is that we are interested, let's say, in the proportion of dog people in the Netherlands. So if you don't like the cat and dog example, you can also think of any other proportion where we have a binary variable underlying, say, the proportion of people who want to buy a product, the proportion of people who have side effects in a medication, the proportion of companies who cheat on their taxes, the proportion of people with a certain gene type. Yeah, just to say that we will use this example, but you can apply this to other contexts as well. So we look at the proportion of dog people, and the proportion can range between 0, that means 0% dog people, and 1, that means 100% dog people in the population. And we don't know this underlying proportion, we don't know the population value. And but we might have a hint about it, we might have an idea. And we can capture this prior knowledge in the prior distribution. The prior distribution is a probability function, probability density function, if it's continuous. And it quantifies the uncertainty about a parameter before data collection. So it quantifies what we know about this parameter, or what we believe to know about this parameter before data collection. If this probability distribution is very wide, we'll see example for this later, this means that we are very uncertain. A lot of parameter values are possible. If this probability distribution is very narrow, this means that we consider only a few parameter values as likely values. Here I brought a few prior distributions that you could use in this case. And really there's, you can grow crazy on this. So the only restriction we have here is that we know our parameter ranges between 0 and 1. So we cannot have more than 100% dog people, for example, and not less than 0%. So as a prior distribution, we need a probability distribution where the support is somewhere between 0 and 1. So it should only assign probabilities to values within this range. But of course, the way these prior distributions can look can be very different. For example, here we have someone who is just very certain, 100% certain that there are as many dog people as cat people. Why? Because this person placed all prior probability on one value, and that is 0.5, which means there are as many dog people as cat people. Now here's someone who did a bit of an interesting thing and assigned a certain probability to 0.6, 0.7, and 0.8, but a probability of 0 to all other values. So this person says, before seeing any data, I believe that there are either 60, 70, or 80% dog people in the population. This is also a valid prior distribution. Now, the other prior distributions that I show here are continuous over the whole range of the parameter. So this person would use a uniform prior between 0 and 1. So basically, this states, I have no clue. I don't know anything. Any proportion is, for me, equally likely a priori. These people here state, well, for example, I do believe that values around 0.5, or here values around 0.25, or here values around 0.75 are more likely than other values, but I don't want to exclude any value. So I assign some, even if it's a low probability, but some probability density in this case to all of the values that the parameter can take. So these are a few ways you can specify your prior distribution. The typical way to define a prior distribution in this case is one of these four. So you would specify a prior distribution on all parameters that can occur. So all of these prior distributions are beta distributions. You don't have to know out of your head what a beta distribution is. But a beta distribution is a very flexible distribution that assigns a probability between values between 0 and 1. And this is the kind of distribution we want here. So in the next step, I want to move with you to the R script that I provided with this workshop, so that you can find your own prior for this scenario. And you can, if you open the R script, I'll do this immediately when I'm finished with this slide. You will see that you can assign two shape parameters to configure your beta distribution. And the shape parameters can take any value between 0 and infinity, so it just has to be positive. And the higher your first shape parameter, the higher will be the peak of the probability distribution. So just play around with it for a few minutes and let me know in the chat, just say yes or okay if you found a probability distribution, a beta distribution that represents your prior beliefs.
We have a first question.
Oh yeah, we have a first question.
Yes, so Anna asked, is the beta distribution more common in general, or does it depend on the question? Yeah,
very, very good question. It depends on the question. So for this problem, where we are looking at a proportion, we're interested in a proportion, the beta distribution is a very common choice. For other questions, for example, if you're interested in a mean, the parameter can range in from -infinity to infinity, technically. So you would, in this case, you wouldn't want to restrict the prior to just 0 and 1, which is, as you can see here, what the beta distribution would do. So then in this case, you would usually use a different prior distribution.
Yeah, I also used a Poisson distribution for counts. So if it's not continuous.
So we'll come to that. There are many different examples.
Yes, great. Actually, this should work for everyone in the sense that you don't need to install any extra packages. So you're only using Bayesian.
Yes.
So it should be very easy on any SR session today.
Yeah. And so here you can see in the code, by the way, here you can see the beta distribution. So it says d beta, that means it's the density function of the beta distribution. And it gives you the density for any value with the two shape parameters of the beta distribution. And this whole command here just makes it plot so that you can actually see your distribution.
But you don't have to specify x or theta, right?
No. The only thing you need to change here is if you want to specify your distribution is just enter a different number here where I have 1, 1.
Okay. So no, just asking because if it's somewhere, it's common names in a way. So if you defined it somewhere else, could it get confused?
No, so the idea is that you specify this once at the start and then you can use it, it will use your prior distribution throughout. So you can see I started with my uniform and uninformed prior distribution, but you might actually have an idea about whether there are more dog people or more cat people. So you can specify a different prior. Anna asked, shape 1 is dog people and shape 2 is cat people. Yes, basically. You can also think of these as counts of dog people or cat people. And Martine said she chose 1.3 and 1.5, leaning a bit towards that there are more cat people, I think. Yeah.
If you use 0.5 for both, you get a weird U shape. Does that
Yes.
mean it means I'm either a cat or a dog person, there's nothing in between?
Yes, actually 0.5 and 0.5 is also prior that people often use for this if they also want to express they don't really know, because it updates very quickly. But we will get to that later. So maybe it's interesting if you choose this prior. It's interesting to follow through and see what our results will do to this. All right. Please just post some sign in the chat if you found your prior.
Or just raise a thumbs up somewhere. That also works.
Kate went with 35 and 25, which she thinks is giving her a probability that the majority are dog people. Yes, that's true.
I think some people are done.
Okay. I was waiting for
some
more
more
replies, but nice. Now everyone. Now replies are coming in. Sorry, I think I should have clarified this before. Really, when you're done, just write "done" in the chat, and then I can see the increasing number of messages, and I get a feeling for where you're standing. But this is great. So everyone found their prior. That's quite exciting. Your first part of Bayesian analysis. So let's move on to the likelihood. So we need the likelihood to do anything in Bayesian statistics. The likelihood shows us how plausible data are given a fixed parameter value. And so the number of successes in a sequence of n independent trials, which we have here, if we ask people, are you a dog person? Yes or no, and we ask a lot of people independently of each other in our sample. So the number of successes in a sequence of n independent trials, each asking a yes/no question, follows a binomial distribution with success parameter theta. So this is just basic probability theory. This is basically the model that the probability model of our data. This is something we need to know. And this is also something, if we want to use Bayesian statistics, and this is also something you will get practice with if you use this more often. So for now, for this example, I'll just tell you that we need a binomial likelihood, and but other examples, other applications will need other likelihoods. So what does this look like? So we have a probability. So we say we want to collect a sample of 5 people. Then 0, 1, 2, 3, 4, or 5 of these people can self-identify as dog people. And the likelihood gives us an idea of how plausible it is that 0, 1, 2, 3, 4, or 5 people are self-identify as dog people in our sample. It does so based on a specific parameter value. So we say here we assume a proportion of 50% dog people in the population. So if there are 50% dog people in the population, how likely is it that in a sample of 5, say 2 will self-identify as dog people? Here we have the same, just with an underlying parameter of 0.8. So here we ask, well, what happens if the parameter is 0.8? How plausible is it that, say, 3 or 4 or 1 person identifies as a dog person in our sample out of 5? And so this is you can find this out using a likelihood function, and in this case, the binomial likelihood. And so you can play around with this again in the R script that I provided. So that's just the next part in the R script. Maybe I should start sharing my other screen. Yeah. So this is the part where you can just play around with likelihood for a minute. And so say we have 5 observations, the probability is, the proportion is 0.5 in the population. Now, then this is, shows me how plausible it is to see, say, 2, 3, 1 dog person in my sample. We can also change this around to say 10. Then we can see this in a sample of 10, or just change the proportion. Then it looks differently again. So you can try this out a bit for yourself.
Angelika, if you go back to this circle from prior knowledge to data, how do you connect these two? So I first need to think, okay, what is my gut feeling of how the world looks like? That's the first distribution. And now I have this other likelihood distribution. That is, where does that fall on this circle?
So the likelihood function basically is your is also part of your model. So in Bayesian statistics, we would define, or most people would define the model as a combination of the likelihood and the prior. And in the likelihood, you have a parameter, and this parameter value, you can see this here, for example, 0.5 or 0.8. This parameter is the parameter we're interested in. And this is also the parameter we put a prior distribution on. So it's basically all at the like definition of the model.
Well, maybe it will come later. So is this probability the same as the theta that is in the previous?
Yeah. So I should have said this, I think. This probability here or here is the theta we had previously.
Okay. Okay, thanks.
And the theta is the same as the proportion of dog people. All right. I hope everyone got to try this out a little. Then we can move on and start making our first predictions. And we will do this with the prior predictive distribution. The prior predictive distribution makes predictions about the plausibility of data, assuming that a model that is prior and likelihood together is correct, what predictions does this model make about possible data? And so here we want to make predictions, but we want to incorporate the uncertainty that we have about our parameter, about the theta, about the proportion of dog people in these predictions. So unlike the likelihood, where we can basically make predictions about what is plausible if the parameter is this or that, a specific value, The prior predictive distribution incorporates the uncertainty about the parameter in the predictions. So what does it do? It weighs the likelihood of all possible observations with the prior across all possible parameter values. So we have the prior distribution, and this shows us how plausible parameter values are before seeing the data. We defined this. You chose your beta values. And we have the likelihood, and this shows us how plausible data are given a fixed parameter value. And so say someone defines only 2 parameter values that are possible, what would we do? We would take the probability of the first value times the likelihood based on this parameter value, plus the probability of the second value that we defined in the prior distribution times the likelihood again. So this is what we would do if we had only 2 possible parameter values in the prior. But usually we have more than 2. So either we need a longer sum, or what happens if we have infinitely many possible values, which is the case if we have a continuous distribution across the parameter space, well, then we have to integrate instead of a sum. And if anyone is not familiar with integrals, just replace this integral with a sum sign, and you should, like, conceptually, you're good.
We got 2 questions.
Oh, yeah.
I think it's good to have them now.
Yes.
So Delia asked the question, previously we checked the theta distribution on the population, while now it's on our sample. Is this correct? I'm not sure, Delia, which one you're referring to.
Yes, so you notice, I'll actually show this here. So here we are talking about the plausibility of data. So on we have possible observations on the x-axis. This was also the case for the likelihood. But for the prior, we have theta on the x-axis, so the parameter value. And so the prior makes makes assumptions, statements about the plausibility of parameter values. Now the prior predictive distribution makes a statement about the plausibility of data values, of observations. And you can also see this if you're like mathematically inclined, that we integrate out the parameter here. Okay, I hope this answers the question. If not, just ask again.
There was another question.
Is,
oh yeah, you can read it yourself.
Yeah, theta would be the 0.5 and the x is the sample of 5. Oh yeah, yeah, I put this I put this here, the equations. So x is always the data values in these equations. For me, you could also write d, anything. And theta, in general, usually Greek letters are the parameters. So that would be, in our case, the underlying proportion that we want to know. And so x would, for example, be 3, as in we observed 3 dog people. All right. So you can compute the prior predictive distribution for this example on your own using the next part of the code. And this might be a little bit more difficult to read but actually it's exactly what we did here. I also color coded the parts of the code so that you can connect them. So we have the prior here, that's a beta distribution. And we have the likelihood here, that's a binomial distribution. And we take the product and we integrate over it. That means we define the integrand here, that's everything between the integral signs here, and then integrate it. Here we do, I have to say this, we do a numeric integration. We just use R's numeric integration function, which is great and is very, very close to what the actual value is. In this case, it would be possible to compute this by hand, but yeah, we would need another hour for this. So we won't do this. But yeah. So you can just follow the code. All right. Maybe you can just write done in the chat when you're done. All right. Yeah. Looks like almost everyone at least got a chance to try it out. Nice. So this is what your prior predictive distribution should look like. Here you can see two examples. I don't know what your prior was, but here I have a beta 2.2 prior or a beta 8.4 prior that tells me something about what parameter values, what proportions of dog people a person, this one or that one, could find plausible. And from these plausible parameter values in combination with the likelihood, we can get to the prior predictive. And you can see that the prior predictive sort of resembles what is going on in the prior. So for example, if I think, say here, that, well, most likely around 50, like the split in the population is about 50-50, then it's also more plausible to observe about half of the people, that half of the people are dog people. If I think that it's more plausible that around 75% of people are dog people, then I would also think that it's more plausible to see 3, 4, or 5 people who self-identify as dog people in a sample of 5. So you should be able to see this for your own prior distribution as well. All right. So everything we've done so far, note that really everything we've done so far was completely without data, without actual data. This is just our model, what we think before seeing any data, and our and predictions that we make from the model, but we haven't seen any data. And now this is the moment where data comes in. So we observe, I now said we observe fictional data with 3 dog people and 2 cat people. There's a line in the code. I actually didn't print this on the slides, but there's a line in the code that defines the number of dog people. And so if you want to change this, if you want to change the data, feel also free to change the data. I will use 3 dog people and 2 cat people, but you can actually change this vector around. Of course, this data is fictional, so I didn't ask any people, but we will now work with this. And the first thing we can do is to look at the marginal likelihood. Marginal likelihood sounds like a very difficult word, and a lot of people have difficulties understanding what this is when they first hear about Bayesian statistics, but it's actually pretty easy because it is just the prior predictive distribution that we just looked at before, evaluated at the observed data. So it tells me how plausible are the observed data under my model. So what do? I had 2 prior predictive distributions before, right, with 2 different priors, and now I collected data with 3 dog people and 2 cat people, and now I just look at how plausible was this observation under my prior predictive. And that's it, that's the marginal likelihood. You've done all the difficult work before, now you can just enjoy the marginal likelihood. And so one reason we need this marginal likelihood is to compute the posterior distribution. And you can see that.
Question.
Yeah.
Just one question. How's everybody doing? Do you think it would make sense to have a 5-minute break? Otherwise, we can always continue. Let's just have a.
Yeah, let's just have a 5-minute break.
Okay, 5 minutes. You can get tea or whatever you want to drink.
Yeah.
And then we'll continue updating our knowledge.
Yes. And I'll be here. So if you want to ask any questions, maybe we can also stop the recording. So if anyone wants to ask questions and not be on the recording. All right, everyone back from the break. So we continue with updating our prior knowledge in the posterior distribution. Now, the posterior distribution is also a probability function. And unlike the prior distribution, it quantifies your uncertainty about a parameter within a specific model after the data collection. Now, this means we started out with a prior, we updated it with data, and now we are at a posterior where we have gained new knowledge about our parameter. And now the question is how to get from prior to posterior. And this is where the famous Bayes rule comes in. And you might have seen this in some way or other already. It's basically a conditional probability formula. And so conceptually, I know equations are always a little bit scary, but let's go through it conceptually. What does it mean? It means exactly what we talked about before. We want to know the knowledge after the data collection, and our knowledge after the data collection is a combination of the knowledge before the data collection and some sort of updating factor. And what is this prior and posterior knowledge exactly? Well, our posterior distribution is the prior distribution times the likelihood divided by the marginal likelihood. I see in the chat that Martine asked what was the question on slide. I just asked in the break whether it's okay if I just show the code on the slides, and people said it was okay. So I'm just going to continue with this. But if you want me to switch to R, just let me know. So we have talked about all these concepts: likelihood, prior distribution, marginal likelihood. And now we just basically insert them in Bayes' theorem, and the outcome is the posterior distribution. So we insert what we knew before about the parameter times, a factor, the likelihood that tells us how our data would come together given a certain parameter, divided by the marginal likelihood. So that's how plausible our data are under any parameter in the model. So if you want to do this in R, you can just continue with the next fragment in the code. And well, first you need to calculate the marginal likelihood and of your data. So this will tell you how plausible are your data under this model. And then you just go over this formula of the posterior distribution. You can again see here it's likelihood times prior divided by marginal likelihood. That's the posterior. And then you can take a look at your posterior and just plot it and see what happens. I'll give you a little bit of time to do this. You can just write done in the chat again. Okay, seems like, yeah, most people are done. By the way, if you go a little bit further in the code, you can also plot the prior and the posterior, which I also did here. So here in blue is the prior, in red is the posterior. I don't know what your prior was, or but yeah, maybe it looks like a little bit like this here. So what we can see is that usually the posterior is a little bit more peaked than the prior. This is because we gained some knowledge. Now, before seeing any data, we were quite uncertain. And now after seeing the data, we have more knowledge. We know more about the parameter value. So we consider less parameter values as likely to be the true parameter. And what you can also see is that the prior influences the posterior. So what we knew before about the parameter value influences what we know afterwards. Now, many people ask, well, is this a problem? Because I might have been just wrong before. So should I now adjust my prior and go back to something else? No, actually, you don't have to. You just learn. So I mean, this is really just the same way we learn in real life. If we are rational people, we can be convinced by good arguments. And here in Bayesian statistics, our data are our argument, basically. So what happens if my prior was wrong? You can see this, for example, here. This prior said, well, I think around 25% of the people are dog people. But in our sample, actually more than 25% of the people were dog people. So our sample said, well, maybe you weren't quite right. And what happens is that the posterior adjusts for this new knowledge. So the posterior is a little bit dragged, like the maximum of the posterior is dragged towards what happens in the sample. And the thing is, right now we had a sample of only 5 observations. 5 observations is nothing in any model. So usually you would have a much bigger sample. And if you have more data, your data will also contain more information, and this information will also be incorporated in the posterior. So the more data you have, the more your posterior will be influenced by this data. In Bayesian, many Bayesians call this the data overwhelms the prior. So as you gather more data, your prior gets less and less and less important. And in the end, basically all that counts is the new knowledge that you gained rather than the knowledge you had from before. So this is actually, I think this is super cool, because going from prior to posterior really represents how we would gain knowledge in real life, I think. And we start out with something we know, and then we get new information and we update our beliefs to that. And this is what is also done in these probability distributions. Anna asks, wouldn't the central limit theorem then expect the distribution to become more bell-shaped? Yes, this is true. Approximately, like if you have a lot of data, you can approximate your posterior distribution usually with a normal distribution. There might be cases where this doesn't work, but in general, yes. All right. Now, of course, what we want to do now we have this new knowledge, and somehow parameter estimation means we want to describe this new knowledge. And this means that usually people are not satisfied with just seeing a posterior distribution. Usually they want to describe this distribution somehow. And of course, one way to do this is using the mean or the median. But one other popular way to do this is using the so-called credible interval. Now, if you think credible interval sounds familiar, you can think of this as a Bayesian confidence interval, if you've heard of confidence intervals. The advantage of the Bayesian credible interval is that it's very easy to interpret. So no difficult interpretations that can go wrong as with the confidence interval. We can just interpret this as, with a probability of X, the parameter lies within this interval. And we define this based on the posterior distribution. For example, the central credible interval contains the central 95% of the posterior distribution. That means we cut off 2.5% on the left side and 2.5% on the right side, and look where these cutoff values lie, and that's our credible interval. Very easy description of the posterior distribution. Now you can get your credible interval, the upper and lower bound again, in the R script. It's just 2 lines of code, actually 3 commands. What we define there is a cumulative probability distribution for this posterior. So we say how much area is covered until here, 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 under the posterior distribution. This is the cumulative posterior cumulative density function of the posterior distribution. And then we ask, well, at what point is this cumulative, does this cumulative density function of the posterior give you a value of 0.025 or 0.975 for 2.5% at each side. And yeah, that's what is computed in the next two elements. Just let me know if you succeeded in executing the code. Someone asked, I thought CI means confidence interval. Is it the same? The Bayesian credible interval is a Bayesian version of the confidence interval. The confidence interval is like is a frequentist concept. I won't go into the details, but it doesn't involve a posterior distribution. And that's the big difference. That's also why we can interpret it easily as with a probability of X%, the parameter lies within this interval. So we don't need to talk about coverage or like with a probability of X%. If we do this a lot of times, then in 95% of the cases, the interval will cover the true value. That's like a very complex interpretation that we don't need here, and that's reserved for the frequentist confidence interval here, but it's conceptually similar. So it gives you an idea about, well, here it's just very clearly the uncertainty around our estimate. Like what are plausible values for the parameter. So the idea is similar, the computation and interpretation, not exactly. All right. So this was Bayesian parameter estimation. I feel like it's been quite a lot already. So just to recap, we went from prior knowledge with the prior distribution and combined this with the likelihood to prior predictive distribution. We made observations and we looked at how good were our predictions by looking at the marginal likelihood. And we updated our prior distributions to a posterior distribution, which is now our new state of knowledge. And so this is also something that is really nice about Bayesian statistics, because what happens now if I collect another batch of data? Well, then yesterday's posterior is today's prior. I can just continue in this circle. So I can just use my posterior as a new prior and just continue all the time around until I get tired of collecting more observations. So this is kind of a nice thing, I think. And we will also see this in Bayesian hypothesis testing or model comparison. So whether you call this part hypothesis testing or model comparison is a bit of a question of where you're coming from and how many competing ideas you have of how the world works. That is, how many competing models. So hypothesis testing is typically when you say, I have two models that I want to compare to ideas of how the world works, which is also similar to null hypothesis significance testing, where I have a null hypothesis and an alternative hypothesis. Bayesian model comparison basically does the same, just with more models usually. And people often use these terms kind of interchangeably. So sometimes they would say model comparison when they mean hypothesis testing, or the other way around.
So Angelika,
Mm-hmm.
if you start with Bayesian statistics and modeling, you always start with parameter estimation?
So the question is, I think if you start learning statistics, I think it's easy to start with parameter estimation. Because it's kind of, you only have to think of one model. If you actually practice Bayesian statistics, then there's, well, I mean, you can do both. You can do either or both. If you do both, usually you would start with model comparison. So basically check, for example, is there an effect or is there no effect? And if there is an effect, then I want to know how big it is. So then I would continue with parameter estimation. So that's the idea. But some people also just don't like model comparison, so they just stick to parameter estimation. All right, there are 3 concepts that I want you to know, and they also belong to this knowledge updating cycle. One is prior model odds, one is base factor, and one is posterior model odds. And you can also already think of where this is probably going to go if something is called prior and something is called posterior. This is where our prior knowledge will be, and this is where our posterior knowledge will be. So let's start with prior model odds. Prior model odds compare the relative plausibility of 2 models before data collection. So now we go one step back, and we imagine that we haven't collected our data yet. So this is still before data collection. And I can, even before data collection, you and we can have different ideas about how the world works. And we can specify our ideas in 2 different models. So for example, someone can say, well, I firmly believe that there are 50% dog people in the population. Nothing else works. And one person can say, well, I'm not so sure everything is possible. So this is an example where 2 people specified 2 different prior distributions. This means they have 2 different models. And now a third person could say, well, I believe more in this person than in that person. I believe that this person is more likely to be right than the other person. Or I can say, well, I don't know. Either one could be right. And this is what is expressed in the prior model odds. So here, for example, a person would assign the same plausibility to each of the models. So the model odds, that is the plausibility of one divided by the plausibility of the other, is 1. Here, the person would say, well, I believe that this person, I believe much more in this person than in that person, more in this model than in that model. And so this is expressed by prior model odds of 1 to 9, for example. Could also be 1 to 10 or 1 to 100, depending on what you want to do. And so usually if people conduct or use Bayesian statistics, they don't express very strong prior odds, but you could do so. For example, if you have high costs attached to one option, or if someone says you have 2 models and one says the person is guilty and the other says the person is innocent, well, it's very bad to say someone is guilty when the person is actually innocent. So you want to be very sure about this. Yeah, you could also express this with prior model odds. You can, yeah. I'll let you specify the prior model odds in the code, but that comes a bit later because it's really just two numbers. So let's first see how they are updated. For this, we will use our frictional data again and look at the updating factor. And so this updating factor is called the Bayes factor. And this is a very, very famous Bayesian quantity. And it tells you how much more likely were the observed data under one model than under the other model. And it can be interpreted as a sort of relative evidence for a model. So basically now we're again at the stage where we compare our model predictions now for each of, say, two models with data. We can calculate the Bayes factor as a ratio of two marginal likelihoods. So for example, we have one model here where we had this marginal likelihood. That's the prior predictive distribution evaluated at the point of the data. So this marginal likelihood under this model. The marginal likelihood under this model. And both of these marginal likelihoods describe how likely it was to observe our specific data under this model. And what the Bayes factor does is to compare these. Just say, how much more likely was it to observe the data under the first model than under the second model? So here, for example, we have two marginal likelihoods. We just divide them by each other and get a Bayes factor of 1.896, which in this case means that the data were 1.896 times more likely to have occurred under the first model than under the second model. So you can do this now in the code if you want. Just go to the R script again. And you already computed the marginal likelihood before for your model with your prior that you set at the very beginning. Now we need a second model, and as a second model, we use something that is very often used in Bayesian hypothesis testing, and that is a model that specifies one specific parameter. So in this case, one where we are absolutely certain that the probability is, or the proportion is 0.5 in the population. So this is basically like a null hypothesis that states the parameter is x, say 0.5, and an alternative hypothesis that states the parameter is, well, something else. And you can compare how likely your data were to occur under each of these models with the Bayes factor. So you take the marginal likelihood under the one model divided by the marginal likelihood under the other model. Just let me know when you have found your Bayes factor. think looks good. All right. Let's look at how we can interpret this Bayes factor. I already said it's sort of an updating factor, but we can also interpret this as evidence. And so if you got a Bayes factor that is larger than 1, this means that there is evidence in favor of model 1. It means that, let's go back to the ratio. The data are more likely to have occurred under model 1 than under model 2. A Bayes factor of smaller than 1, so it's a ratio, so the smallest value it can take is 0, or not exactly 0, but it gets close to 0. So if the Bayes factor is smaller than 1, it means that there's evidence in favor of the second model. So the data are more likely to have occurred under the second model. If the Bayes factor is exactly 1, there's no evidence. So we just don't know, and this can happen. Well, but it is very unlikely that your Bayes factor will hit exactly 1. It would hit exactly 1 if you compare a model, the marginal likelihood of one model against the marginal likelihood of exactly the same model. Then you're guaranteed to get a Bayes factor of 1. Otherwise, it will differ from 1, at least a little bit. And now the question is, well, it tells me something about how much evidence there is in the data for one model or the other one, but how much evidence is convincing? And so there's, so actually this quantity is a continuous quantity. So you can, you shouldn't really you don't really need to categorize it. But people still do it. And if people do it, they do it usually something like this, where they say, well, a Bayes factor between 1 and 3 is anecdotal, a Bayes factor between 3 and 10 is moderate, a Bayes factor between 10 and 30 is strong evidence, and then very strong and extreme evidence. Of course, this is a question, like what you consider strong evidence is a question of what research area are you in, what application area, what are your stakes. So for example, say you're in some sort of industry engineering scenario, and you collect evidence for, say, one process, whether one process somehow works better than a different process, but switching from one process to the other costs a lot. So in order to switch from one process to the other, you would want to have a lot of evidence in favor of this other process, this new process. You would really want to know that it works better. And you can think of this the same way for Bayes factors. So the higher your stakes are, the more evidence you would want. So these classifications, they are often used in scientific papers. Oh, we found moderate evidence in favor of our hypothesis. And this is okay. Just keep in mind that it's a continuous quantity. So someone in a different scenario might not consider the evidence that you have as moderate. They might consider it as completely insufficient. All right. Final Bayesian concept is posterior model odds. Now, the posterior model odds compare the relative plausibility of two models after the data collection. So they're kind of the equivalent, like you can think of this like prior distribution and posterior distribution are knowledge before and after data collection on the parameter estimation side, and prior and posterior model odds are knowledge about the models before and after data collection. So how do we get there? I already announced that a Bayes factor is an updating factor. And this is where the updating comes in. The Bayes factor updates your prior model odds to posterior model odds. So say someone had prior model odds of 1, so equal plausibility of both models. And then the Bayes factor is 1.46 in favor of the first model. Then we just multiply the prior model odds with the Bayes factor. Notice that the prior model odds should be formulated in the same way. So basically prior model odds for model 1 versus model 2. And the Bayes factor should also be model 1 versus model 2, not the other way around. Or if you do the other way around, then do both the other way around. So 2, 1 and 2, 1. So the posterior model odds are the prior model odds times the Bayes factor. And so here they are 1.46 to 1 in favor of this model. And you can see this a little bit with the pie chart. So this was the original state of the knowledge. And now this is the updated stage of the knowledge. And so what I like about this is that, again, it's very easy first of all, it again shows this knowledge updating, this very intuitive going from prior knowledge to posterior knowledge. And it also provides another view of the Bayes factor. And that is, say someone is a skeptic and someone really doesn't believe in, say, this model at the start. And they have prior odds 100 to 1 for this, or 99 to 1 for this model. Then you can easily compute what Bayes factor do you need to convince them. So this is also an idea of how to interpret your Bayes factor. If your Bayes factor is, say, 3, you won't convince someone with prior odds 10 to 1 against the model that won in your comparison. So if you're in a field or in an area with a lot of conflict, you should rather have higher Bayes factors than if people are easily convinced. Okay, this is how it's done in the code. You can just follow me here. You can specify your prior model probabilities. I just specified them as equal. By the way, usually these prior model odds are defined as like one probability divided by another probability, as usually like a definition of odds, but it really doesn't matter. You can also write 1 and 9 here, or like these don't really have to be probabilities in this case to determine the prior model odds. And well, then we take the prior odds times the Bayes factor and we arrive at the posterior model odds. That's it, done. So we went through the whole Bayesian updating cycle once with all these different Bayesian concepts, which I hope you have a bit of a better understanding now. Now,
I have a question.
Yeah, maybe this is a good point for questions.
Like maybe just from a convincing factor, if you are trying to convince someone, would you rather put the model that is you want to convince people on the side so that the number becomes big, because it, you know, it's in favor or against, like it goes below 1. But if you have a tiny number, maybe that like 0.5 is not as convincing as 2 times, because if it can go up to, I don't know, 100 or something.
This is a very very interesting psychological question. I don't know. So what people often do is, because so if you would want the base vector to be symmetric, you would have to take the log. So on a log scale, you can see that a base vector of 0.5 is exactly as good as a base vector of 2. But it's just more difficult to interpret. So what people often do is, when they say, well, look, I found evidence for or against this model, then they just use the base vector as a ratio. So you can say this model is model 1, this model is model 2, or the other way around. That's completely arbitrary. And then they often report their analysis in a way that the number is above 1, and say I got a base vector of 3 against the null hypothesis, which is, by the way, I can't believe I didn't mention this. This is one of the most mentioned advantages of Bayesian hypothesis testing. Now it's really hypothesis testing in comparison to null hypothesis significance testing, like the frequentist way, is that you can measure evidence for the null hypothesis. So your null hypothesis is represented by one model. And if the base vector is in favor of that null hypothesis, you have evidence in favor of the null hypothesis. This is something we cannot do with traditional frequentist hypothesis testing. And because there we don't have a specified alternative, essentially. Yeah, so very good question. Yeah, just a few final slides. So I walked you through one very, very simple case. And I'm sure a few of you are wondering, well, am I ever going to use a binomial case in my life? I'm not interested in the proportion of dog people or any other proportion in the world. I am more interested in complex processes. I have a lot of parameters. I have, very complex data structures. So what can I take away from this course or from this workshop? And well, first of all, yes, we looked at a very simple case, but it is like you can use this framework for very, very complex cases. Bayesian statistics, the Bayesian statistical framework can be applied to extremely complicated scenarios, say hierarchical data, many parameters, nonlinear relationships. It is actually, so personally, I find the Bayesian framework extremely flexible. So as long as you have an idea about how your data came together, that is about as soon as you can find a likelihood function for your data, then you're good, basically. Then you put priors on your parameters and you estimate the model. And then you just go for even a very, very complex model. You go through the same knowledge updating steps as we did today. And of course, you don't have just one parameter, but you might have many parameters. But conceptually, it's all the same. So it's all prior. You look at prior distribution. You specify prior distributions. You specify, or you get posterior distributions. You can get base vectors for very complex models. These models also don't have to be nested, which is often the case with like frequentist equivalence. So you're very, very flexible with this. And if I had more time, I would show you more complex examples. But for now, yeah. There's one question. Do you expect to use EDA to define your prior? What is EDA?
Explorative data analysis.
Exploratory data analysis. Oh, okay. Sorry. I didn't know this abbreviation. Yes, you can. You can use previous data to define your prior. You can also, in every Bayesian, like no matter whether you're in hypothesis testing or in parameter estimation, you can also always continuously update. So you can start out with something, something that is uninformed, and then go to something that is more informed just by continuously updating. There's one, you might have heard something about empirical Bayes and empirical priors. So this is for people who don't like incorporating their own knowledge. They use a tiny fraction of the data to specify their priors. This is also one way to go. Well, but so I also want to be realistic. So I told you about all the advantages. So I should also mention something, at least something bad, and that is usually the computation time. So you've seen this integral in the computation of the marginal likelihood. Yeah, this is a problem. This is uncomfortable, and this makes it very difficult to solve Bayesian problems analytically, because integrals are more difficult to solve, for examples, than derivatives, or to find than the derivatives in math. And so you need numerical approximations to this integral. And this gets more and more complex as you have more and more parameters. So, and this doesn't mean it's impossible, not at all. There's a lot that's possible. But if you have a very complex model with a likelihood function that takes a lot of time to evaluate, it will also take a lot of time to evaluate these integrals, or to simulate data from, or to sample data from your posterior, because this is what you actually do. But so it will, the more complex your model is, the more computationally expensive does it get. And this is just like, if you stay in the region of t-tests or ANOVAs, this is not a problem at all. Like even multiple regression, still fine. But if you go to something huge and big hierarchical model, many layers of data, then it might take hours or even days to compute. So just keep that in mind. If you run a Bayesian model and it takes a long time, this might be normal. Then this might not be an error in your code. Yeah, all right. But I also, this makes everything sound super complex and very computationally intensive, and so you're probably wondering, well, where do I start? All these complex models, where should I start? And well, we're at Our Lady, so I'll start with the R side of things. There are a lot of R packages that can help you with starting out and computing Bayesian analyses. So if you come from a statistical perspective, from hypothesis testing, and you're used to, say, t-tests, ANOVAs, regression models, then I can really recommend the Bayes factor package, which provides default solutions to a lot of typical hypothesis tests. So if you, for example, want to compute something like an ANOVA, but then please in Bayes, then this is what the Bayes vector package does for you. And it's really good. It's very well known. Yeah, so you can trust it. If you're more of a hierarchical modeling, mixed model type, if you're more interested in generalized linear models, then I can recommend BRMS as a start, which is also yeah, all of these packages are really good, really established, and you can just also BRMS gives you a lot of flexibility, for example, with regard to your priors. It is only for parameter estimation, though. If you want to do hypothesis testing in this area, like generalized linear models, I can recommend BAS. That is an abbreviation for Bayesian adaptive sampling, and is a package that will give you Bayesian model comparisons for basically generalized linear models. Then a very, very flexible R package is RStan. It is actually, so Stan is another probabilistic programming language. So it's not R, but a different programming language, which is based on C++. And RStan communicates with this programming language. And you can basically, you use RStan if you want to define your own model. If you really want to, you have an idea for a model for how your data came together, and you want to be completely flexible. Then you have basically a text file where you specify the model, and you can use R. You can read this into R using RStan, using Stan to evaluate well, your data to fit the model with your data. So this is, I would say, this is the most advanced pretty much you can get with this. Now these are just some helper packages. I'll leave them here. It's like some are for plotting, some are for getting Bayes vectors, or statistics of the posterior distribution, like the mean of the posterior. Yeah, there are many more. So if in doubt, just Google, this is what I want to do, plus Bayes, and plus something R package, and check out if someone has already done this before you start coding. If you think that all of this was kind of nice, but also too fast and too little, then I can also recommend going to textbooks. These are some of my favorites. There are also many more, so just check out whatever you like. So doing Bayesian data analysis is pretty much of an all-rounder. It is a very big book, but also written for yeah, people without a math degree. So there's a lot of text to explain equations, and it is very comprehensive. So it gives you a good overview of both conceptual ideas and also some programming. If you, well, don't want to go that deep, or actually it also goes pretty far, but I think it's even stronger on the conceptual side. I can really recommend statistical rethinking. This is also especially good if you come from frequentist hypothesis testing. So if you're used to, I don't know, calculating regular t-tests, ANOVAs, whatever, this is what this book assumes, that this is where you're coming from. And it basically tells you, so this is where you're coming from, and this is how Bayesian, the Bayesian framework differs from that. Now, this one, the third one, Bayesian data analysis, is a bit of like a more mathematical approach, and it goes deeper on the mathematical and programming aspect of things. So it is really, really comprehensive. It's written by the Pope of Bayesian statistics, Andrew Gell-Mann, so it is very comprehensive, but also not necessarily an easy read if you are not familiar with reading equations. Yeah, and this last one was co-written also by my PhD thesis supervisor, Erik-Jan Wagemakers. It's, I would say, the most on the application side. So in this book tells you how to define your own models in, well, cognitive modeling. That's a discipline in psychology where you use mathematical models to describe basically what people do or how people think. But it has, so I like this book because it has really good short conceptual introductions to all the key concepts. And it's also, it gives very, very brief and good application examples in each chapter. So these last two books are also available, like the Bayesian data analysis book is actually also available for free online. The Bayesian cognitive modeling book is, is at least partly available for free. Yeah, I'll stop with this, slightly over time. I think it was a lot to take in, and we were probably pretty exhausted. But I hope that one thing that hopefully came across was that it is, so Bayesian statistics in its core is actually very intuitive and works very much like common sense. So that's why I put this quote here, not to tell you how easy everything is, because that's mathematically, no, it's not always that easy. But to remind you that even if things look difficult, they are conceptually often very easy. And the quote is, "The theory of probabilities is basically just common sense reduced to calculus. It makes one appreciate with exactness that which accurate minds feel with a sort of instinct, often without being able to account for it." And I think this is exactly what Bayesian statistics does. And I hope you, may see this too now or in the future when you're maybe working with it. So thanks. And I'll answer the questions in the chat now, but maybe we can stop the recording.
Yeah, sure.